we're going to start by thinking about how to combine small velocities. And a lot of this will be common sense, and that's good. But what we're going to see is that the common sense way to add velocities will break down, and we'll need a new technique for doing so. To have a specific case to talk about, we'll think about, let's say, Alice, a person, throwing a tennis ball. And Alice is capable of throwing the ball at 3 miles per hour. Okay, so if Alice is then standing on the ground, we'll draw Alice here, A for Alice, and she's throwing a ball at 3 miles per hour relative to the ground. Eventually, our goal is going to be to see how fast the ball moves relative to the ground if Alice is throwing the ball from a platform that's moving, say a train. So we'll start with Alice on a train and have the train be at rest. Okay, so here's our train, and here's Alice. And we'll say that the train's velocity is 0. And it's at rest relative to the ground. Okay. And in this case, she throws the ball with the same strength as before. So she's going to have that ball move 3 miles per hour relative to the train, but also that is 3 miles per hour relative to the ground because the train is at rest relative to the ground. So the question then becomes, well, what is the speed of the ball going to be if the train is moving and if Alice throws the ball using the same power as her last throw? So once again, we'll draw Alice on the train, but this time we'll let the train move like this. And given that we know the train is moving at 21 miles per hour relative to the ground, and we know that Alice can throw the ball at 3 miles per hour relative to the train, we want to know what is the speed of the ball relative to the ground. And your intuition almost certainly tells you that you just want to add those two numbers together because she's throwing the ball to the right and the train is moving to the right. So the ball is therefore moving to the right with the sum of those two speeds, 21 plus 3 miles per hour equals 24 miles per hour. And indeed, the speed of the ball is 24 miles per hour to the right relative to the ground. We're going to introduce a notation that allows us to generalize this idea. And you'll notice that I've already written v with a subscript train comma ground when describing the velocity of the train relative to the ground. And we're going to keep that notation where we have two subscripts, the first being the subscript of the object and the second of the reference frame. So v train ground means train relative to ground, and we can therefore write v ball train and v ball ground to represent the ball speed relative to the train and the ball speed relative to the ground, respectively. And then rather than writing all these words out every time, we can always abbreviate in the following way. So we have VBG, V ball ground, equals VBT plus VTG, ball relative to train plus train relative to ground. It turns out that this way of combining velocities is correct at small velocities, but we'll soon see that there's a problem with this approach at high speeds, specifically speeds approaching that of the speed of light. Although in this example, we're talking about a ball and a train, this idea of how to combine small velocities works for any objects and any reference frames. So we can generalize this idea by writing Vxz, the velocity of object x relative to frame z, is equal to Vxy, the velocity of x relative to y, plus Vyz, the velocity of y relative to z. And we'll call this our non-relativistic velocity addition law. Here, non-relativistic just means speed slow compared to the speed of light. A little mnemonic for remembering this is if at the end of the day you want to know x relative to z, then you're going to have to combine two other velocities where x and z are on the outside. So on the first term, it's x relative to y and y relative to z, but it could be x relative to anything and that anything relative to z. So in other words, you could put any frame of reference here and any object that you want here, they just have to match each other. So you have v x z is vx relative to something, and v of that something relative to z. Now, this is a class about special relativity, which means we're going to investigate objects that move near the speed of light. This velocity addition law is non-relativistic, meaning that it only works approximately at speeds that are slow compared to the speed of light. In another video, we'll discuss why this velocity doesn't work at all speeds, and it only works at low speeds low compared to the speed of light. But take a minute to look at this equation and see if you can think of a scenario in which this equation clearly cannot give the correct answer for how you combine speeds. And you might think about scenarios that involve high speeds, because that's where we know this law will break down.